In this second part, we will assemble a single machine infinite bus or SMIB model with the Open Instance Power System library. So the OpenIPSL library is a library for phasor time domain simulation of power system models developed in Modelica. Currently, the library is maintained by our lab, the ALSET lab, at Rensselaer Polytechnic Institute. So the main idea of this part of the tutorial is that we will be given the information of the static and the dynamic model in PSSC, and we will create an equivalent model in Modelica using the aforementioned library. For this tutorial, we will use the latest release of the OpenIPSL library version 2.0, and we will use the Modelica IDE Daimola. However, the steps that we will do are the same as with the previous release, OpenIPSL 1.5.0. And this model has, and if you develop the model with this version of the library, you get compatibility with the open source IDE OpenModelica. So we have done it. We have done this ourselves, and we tested the model with the release 1.16.2. We would like to emphasize that the power flow structure will be created after assembling the model. So we assume that in general, the Modelica model already exists before inserting the power flow structure to it. So in case you are creating or you already have an existing model and you would like to incorporate the power flow structure, we recommend to avoid strange patterns in the component names and to name the generator models according to the buses they are connected to. Basically, this tutorial and the way we will name variables and generators, lines, etc. represents what we think it's a good practice for developing power system models with our library. Okay, so now we will assemble as an SMIB model from scratch. So here we have on the right Daimola, and on the left we have the documentation that is provided together with the GitHub repo. So first of all, we would load the library. The version that we will use is the OpenIPSL 2.0, but the procedure that it's described in the Google Docs is exactly the same, but for the version 1.5.0. So you shouldn't have any problem in following this step-by-step procedure with that version. Also, if you want to use OpenModelica, then we recommend you to stick with the 1.5.0 version shown here in this tutorial. So let me submit this back. So now let's go and create a new package, and the package will be called SMIB. And it's important that we deactivate this checkbox here, because we would like to have the contents of the package within several files, not within just one .mo file. Why? Basically because we will write the power flow records later in different mo files, and in order for our model to be ordered and nice to read, it's important to have the package components in different files. So let's now go inside this package, the SMIB package, and create a new model, and that model will be called SMIB_base_case. And we will add a new sub package here that would be called generation units. So here the same, we don't want to save the contents of the package in one file, and that's pretty much it. So now we go inside generation units and we will create two generators. So let's see here that the SMIB system, whose schematic is here on the right, has two generators, one load, 4 transmission lines, 4 buses. So we would like to create first these generation units, and to do so we will go to the sub package and we'll create a new model called Gen01. So that would be for generator 1. Let's create another one for Gen02. So for Gen01, we double click the new model and we will drag and drop from OpenIPSL electrical machines PSSC, we will drag and drop a gen row component. So let's enlarge this a little bit so that we can read the name of each of these, the variables coming out of these pins. And once we have this, we will go to the text layer in Gen01 and we will right below extends OpenIPSL.interfaces.generator. So why are we doing this? Well, basically because this generator interface has already the power flow variables that must be linked to a regenerator unit, and it also has a nice icon for all of our units. So that's regarding the extension that we have to make on Gen01. If we go to the graphical layer, we'll see that it also added a terminal pin. So we will connect the blue pin on the gen row block to the terminal pin here. And the other thing that we have to do is to connect the different the pins to the input of this gen row block. So here we are not going to model turbine governor system, so we connect PMEC 0 to PMEC, and likewise we are not going to include an excitation system, so we connect EFD 0 to the input EFD. So that's it for gen row. And another thing that we have to do here before I forget is to populate the numerical values. So here let's do it first for the numbers. So the base power, as is shown here on the left, is 100 MVA. 100. T prime D0 is 5. T double prime D0. So that's the one that T double prime D0 is 0.07, sorry. T double prime Q0 is this one, 0.0900. The inertia constant is 4.28. The speed damping is 0. The XD is 1.84. XQ is 1.75. XD prime is 0.41. XD double prime is 0.2. XQ double prime is also 0.2. The leakage reactance is 0.12. The saturation factor on 1 per unit is 0.11. And likewise, at 1.2 per unit, it's 0.39. The armature resistance is 0, so we'll keep that default value, or maybe let's override it since it's 0. X prime Q is 0.6. So X prime Q is here. And T prime Q0, so the Q axis T prime Q0 is 0.9. And I think that's it for the numerical values of the generator. So let me make sure I didn't confuse this. So you would find screenshots of the values here. So let me go here just to confirm Everything is okay. TPQ 0.9. Yep. So I didn't make a mess out of this. So that's it for gen row. So for the numerical values. So now here on PowerFlow data, what we will do is something that is called propagation. So propagation means that the values for this, the values of this block will be provided on an upper layer, on where the containing model is located. So P0, we'll say that will be given by P0. The same for Q0. The same for B0. And we'll do it like for angle knot as well. So that's it for the model. So let's save it inside a directory that I called smib_tutorial. And that's it for the gen row. For gen 01 that has a gen row synchronous machine model. So now let's move to gen 02, and we will do a similar procedure here. So first we will extend the model. So model gen 02 extends OpenIPSL that interfaces the generator. So that's pretty straightforward. And Gen 02 in this system is the slack bus. So we can use for the swing bus, we can use the Gen CLS model that here has a nice icon representing an infinite bus. And let's enlarge it a little bit more. So let's connect this the blue pin to the PW pin connector of the generator interface. And for the values, we can see the values here on the left. So we need to specify the machine base 100 MVAs, inertia constant 5 seconds, damping constant 0. Actually, let's do it with 4 decimal figures. Armature resistance 0, and X source would be here the direct access transient reactance that is 0.2. So yeah, it's basically it for the numerical values of the generator. But if you're using the 1.5 version of OpenIPSL, you can easily notice that you can do the propagation of the PowerFlow variables right here, but that view is locked on the new version of the library. So to overcome this problem, it's pretty simple. What we need to do, we go to the text layer. So you can observe here that the values that we have, the numerical values that we have passed, have been changed here. So what we will do is to do the propagation directly here. So P0 will be P0, then Q0 is Q0, then B0 is B0, and angle knot is angle knot. Okay, let's save our model and let's return to the graphical layer. Double click on the component and we can observe here that the values for initial active reactive power, voltage magnitude, and voltage angle have been propagated by these variables here. So that's it for the two generator models. Pretty straightforward process. And now let's go to the canvas of our SMIB model, where we will drag and drop a generator 1 component here. So let's have a look into the one line diagram of the SMIB system. So generator 1 is the one here on the left, and the rightmost generator is generator 2. So just let's save it here for once. Okay, now let's place the generators on opposite sides, and just for to make this a little bit more illustrative, let's click on both generators and display PowerFlow to both of them. So now we have on the red text we have the active power, and on green we have the reactive power that the generator is providing. That's it for the generators. Now we have to connect the buses. So for the buses, we go to OpenIPSL electrical bus, we have two options, bus and bus ext. So I'd like to use bus, and we need 4 of this. So let's, I would say more or less here. So this for the one that is called bus 2, and one more here for bus, what is called bus 4. So let's go here and change the name. So this one, the leftmost is BO1, this one is BO2, then this one in the middle is BO3, and finally this one is BO4. So that's it for the buses. Now for the lines, we go to branches, electrical branches, and we drag and drop 4 PW line components. So we have one line here, then one here on top, another one here on the bottom, and the next one close to it, connecting buses 4 and 2. And for getting the parameters of these buses, we can go of the lines, we go to our document and we see that the line connecting bus 1 and 3 should be called line O_01. So let's do the connections actually. So let's connect a generator gen 01 to bus 1, and then line 01 to buses 1 and 3, and the values here. So the resistance is 0.001 in per unit, the reactance is 0.2, and actually let's add another figure here. The GMB are given as, we have no G, MB is 0, so let's set both values as 0. And here it's important to mention that in some cases, for example in PSSC, you input the conductance and the susceptance values as they are, so that's what you input into the model. But here in Daimler you have to input G halves of P/2. So that's why here it says shouldn't have susceptance. So for example, if the shouldn't have susceptance for this line was 0.1 in PSSC, you would have to input 0.1 divided by 2 on OpenIPSL. Okay. So, I didn't save. So let's input the values again. Sorry about that. Let's add another figure here. And that's it. So that's it for line 1. So now we have line 2 connecting buses 3 and 2. So line 2 happens to be this one on top. Let's change the name really quick. And the resistance for this line is 0.01. The reactance is 0.2. In GMB, both are 0. Okay, that's it for line 2. Then line 3 connects buses 3 and 4. So line 3 goes between this bus here and this bus here. And let's change the name. Line 03. R is 0.0005. R is 0.1. And GMB, as in the previous case, there are zeros. Okay. Finally, line 4 has to be this one, connecting buses 4 and 2. So let's just move it here. And since I would like this to be as pretty as it can, let's move bus 3 a little bit to the left, and bus 2 a little bit to the right. And this we can move it a tiny bit. Yep. So this is line 4, and the parameters of line 4, the electrical parameters, are exactly the same as for line 3. So this is 0.005, this says 0.1, G is 0, and B is 0 as well. So that's it for the lines in the system. But if we check the one line diagram here, there are two components that we still need to add. So one of them is the load. So we go to electrical loads, PSSE load here. We can drag and drop it somewhere on the canvas. And the load is connected to bus 3. So the most simple connection is just here with this line. And we don't have any parameters for the load, since, well, basically the parameters that we need to input will be given by the power flow result. So that will be added later. And we need a fault to add some dynamics. So fault components can be found under electrical events. Here we drag and drop a PW fault that we will connect to bus 4. So let me just move this here. And here we can observe that PW fault would be connected here. So that's it. The parameters of PW fault, as you can see here, are the following. So R is 0.01, X is 0.1, T1 is 1, and the closing time T2 is 1.1. Okay. Then this almost completes the SMIB model. We need to add a node block that, if you're familiar with Sim Power Systems or with Simscape Electrical, it's the equivalent to the Power GUI block that you have to add in Simulink to simulate your electrical models. That is the system-based block. So that is found under electrical here on top. And that would conclude our model. So let's, just to make it look as it is in the document, let's click all of these buses and let's check the box to display the power flow value. So now let's save our SMIB base case, and that's it. So then after this we will have to add the power flow records into